you will complain that we have lost any intuitive feeling about what is going on, and what our next goal is to actually derive a different quantity which connects with classical ideas. We want to obtain something which we call gamma, capital gamma of phi classical of x. Okay. Now what we want to say is something like this. We want that. So what do we mean by such an action? So recall our dominance by classical paths. So I need not have written this want, okay. So recall dominance by classical paths, where we found that the transition amplitude is e raised to I times the action on the classical path, right, and times some other stuff. In the classical limit, this is what we found. If somehow the action was such that it was dominated by mass of a tennis ball or whatever, then its action would just come out and the answer would be just proportional to this. So we want here to define expect that when I do all this integration, I should come out with an overall just e raised. So there is integration here, but it gives this answer. Okay, this is also how some of the thermodynamic potentials are defined. Gibbs free energy. You have to average over dp, you do the phase space integral of the partition function, but then the left hand side gives the free energy in the exponent, e to the minus Gibbs free energy is equal to integral dx dp of e raised to, so beta of course, e raised to minus beta h, okay, where what remains is its dependence on volume something. This is all that remains. So in a similar way, so the point is you integrated out all the detailed degrees of freedom and then you come out with a potential which when you minimize you see, I'm sure this is completely wrong, but I should have brushed up before coming. But you can, so what do we have for, what are the relations? P equal to minus df by dv, something like this, right, and I think that's correct. So So you want a potential, what I mean is a classical potential of some kind, which when you vary with respect to its argument, you get your desired quantities out of it. So after you have integrated out all the details, the final answer depends only on the extensive variables. The volume is an extensive variable in thermodynamics. Pressure is a local variable, intensive variable. So you can vary that potential with respect to the extensive variable and get a intensive variable as the answer. Similarly here, we expect that after all the complicated stuff here is over, I come out with a clean and neat functional which mimics the classical behavior, okay, except for the problem that this is also a functional of phi. So what is this phi and what is that phi, because this phi is all being integrated over, okay. So I have to somehow find a remainder extensive variable which remains after all the integration here is carried out. This is done by a clever method called Legendre transform, and beautifully enough there is a relationship between the extensive variable we expect classically and the variables we get from this W of j. So the first observation is that the Green's function is twice variation of the generating function. So I am just trying to announce to you the result. We somehow want an object gamma which is going to be the quantum version or the quantum corrected version of S, the good old action of classical mechanics, but now it is function of some slightly different argument. So if this was your naive field, this will be dressed up quantum field in some sense, but it will have classical values, and the gamma will be the effective action for that system. Okay. This is the idea. So then you can see the whole system as evolving as if it's a classical system in terms of some argument called phi classical. So the question is, how do you link the two? So as I said earlier, it's like the potentials one defines in thermodynamics. It is not the naive classical field that you would have put inside the ordinary action. It is dressed up by quantum mechanics. It will be a classical variable. It will be classical variable, but not what you would have expected naively classically. It encapsulates in it the quantum effects, and the function gamma encapsulates all the quantum effects, so that now you can evolve this quantum system as if it is classical. You can study the quantum system as if it is classical by just varying studying Euler-Lagrange equation. Euler-Lagrange equation says that on the classical trajectory, variation of the action is 0. So that is what will happen if you do this. So this is a tall claim, nobody actually achieves this, but the point is you can formally define such a object, and you can get reasonably good estimates of it in perturbation theory for all the leading terms. So finally we will find that in principle gamma is a functional of a field which has encoded all the quantum effects. Actually it is only a variable, so I don't know why we should not say that phi encodes anything. It's just an argument of the functional. So is a functional which encodes all the quantum effect in terms of a function phi classical. We keep calling it classical simply because we are going to treat it as classical, such that the quantum system can be studied as above. Okay. So we will find that gamma will be so to give an example, start with S of phi equal to integral d4x d mu phi minus some u of phi, say minus say m square phi square minus lambda phi to the 4, let us say. Let's suppose we stop there. The gamma will come out okay. It will be, but begins with it will look similar, but then it will have more complicated terms in it, because the effects of the phi to the 4 coupling will m square phi square. Okay. So the and there could be a z in front, which can also be function of phi classical. There would be a wave function renormalization of the fields, and this is how it will look. So it will look similar, but it will have captured all the quantum effects. Now you may ask, why are we struggling to do all this? And the answer is in two parts. In the simpler situations, it allows us to determine the ground state of the system, the collective ground state of the system. Okay. So uses determining the now we tell children that if you put a negative mass squared, then you have a, symmetry breaking potential and all this. So all this is high school algebra. That thing can be rigorously defined, obtained if you do this. If you calculate, so if you put negative mass squared, then you can, if you calculate the effective action correctly, you will actually find that the minimum of the potential is at the correct non-zero value of phi, and it will not be the trivial square root lambda over m over square root lambda or whatever you find from here. So determining the correct ground state of the system, this is usually done by, so assuming translation invariance. So we set all derivative terms to 0. And then we get gamma of phi classical to go over to simply being equal to minus integral of a weak phi classical d4x. Minus sign because gamma has the form of t minus v after all, right? Integral, good old Lagrangian definition. The t part will get set to 0. All the derivative terms, this gamma can be a very unwieldy beast. It can have all kinds of high level derivatives. All of those get set to 0, and you will be left with this v phi classical, which has only polynomials, so only powers of, so this has no derivatives. So this is phi classical, d mu phi classical if you like. But this is only function of, if you, and this we call V effective, we call it effective potential. And the vacuum expectation value that we expect from that translation invariant vacuum so whatever that gives is the ground state value of phi. But interestingly, you can also find other non-trivial solutions. So this is use number 1, but you can also find ground states that are not translation invariant. But time independent, otherwise you will not have a ground state. So phi dot equal to 0. So all the quantum effects are encoded in the coefficients of this effective potential.
I get a value for phi classical.
Yes.
That is.
That will be the expectation value of the field. That will be the vacuum expectation value of the field. Right. Such that phi gs will be equal to where this will be the correct vacuum also. Of course, vacuum is not the correct word, ground state is the correct word. but people use the word vacuum. Vacuum means there should be nothing, but what you begin to find is that there are a lot of things lurking in the vacuum. But anyway, at least it will not have any particle-like excitations of the phi field. That is what we mean by vacuum. Right, so phi will have a value, but there will not be particles whizzing around. So in that sense, it's not free of everything, but it certainly doesn't have excitations moving about. And this is our current enigma, because the electroweak theory is supposed to have a non-zero Higgs field pervading us like the good old ether. Okay. And the Higgs field they observed in LHC was the first excitation above this ether. So we are right now living in a Higgs ether with a non-zero value for phi. And nobody has been able to get rid of this ether idea. And the ether idea looks obviously wrong because some picture like this. Sorry, I should draw it through the center. So the thing is, you are somewhere here. But if it is so, then this is the V effective of electroweak theory. So this is phi Higgs, and this is ground state value. The ground state value determines the masses of everything. It enters into W and Z boson masses, everybody's mass. Now the point is that all of this is at TeV scale. You calculate it at least in like hundreds of. This value is some 200 GeV. Okay. So these values can be thought of in like hundreds of GeV. 100 GeV, 200 GeV to the fourth power because it's density. You can set it, you can say that exactly when G is 250 GeV is where the electroweak vacuum is, and at that vacuum the V effective should be 0, should be the ground state, no energy. If you do this, then standard model works, but there is a slight ticklish problem, which is that all this scale is in GeV scale, but if you have tiny mistake in it to 15th decimal point, it will have residual vacuum energy left. Okay. That vacuum energy can be seen by gravity, which would appear as cosmological constant. So cosmological constant today has the so-called Einstein's famous lambda is today approximately equal to 10 to the minus 11 electron volt to the fourth power. And so in GeV units you have to put 36 here, right? So minus 47 . So today we actually observe vacuum density, vacuum energy density of the order of 10 raised to minus 47 GeV to the 4. This thing requires you to set it to 0 in hundreds of GeV units, so you don't care if this much is residual. But there is a conceptual problem. Why exactly this amount is left over? If there was an error in this thing being set to 0 exactly, there should be maybe 0.7 GeV to the 4 left over, okay? Maybe millionth of, maybe MeV to the 4th left over. But what is left over is stupendously small on the GeV scale, and it is non-zero, it has a value. So you have to tune this to this. This is like our government trying to check your 1 rupee transaction through money pay, so it is as if the government's budget would get reset by whether you bought a chocolate today or not. Well, so that is extreme fine tuning, that it should have been, if it was really determined by this physics, then it should have been in some high scale. At that scale it is 0, so you would say, well, there is no other physics intervening between electroweak and everything else we know. It is electromagnetism at lower scale, which is exactly massless and so on. So where does this energy come from? It should have been ideally 0. If it was 0, then everybody would be happy, because then you would say, oh, supersymmetry is a principle which requires vacuum energy to be exactly 0. So you would have said, oh, it is 0 because of supersymmetry. But it is non-zero and it is stuck at some strange value. So now you have to try to say, yeah, but supersymmetry is actually broken very, very far away in such a way that it shines a little light here, like Birbal's khichdi or something. So it's exactly, but then you have to then tune why it is over there so that it produces this. So there are a lot of, this is how we make our living, making theories for this. So you are welcome to join. Lot to be done here. So this is an open problem, but this is the machinery that allows you to determine it directly, determine it systematically. But there are more, since I have got on the topic, let me just say there are more interesting things that you can compute from the effective potential, where you don't set all derivatives 0, but you set the time derivative to 0. So your time independent state, but not translation invariant. So in this case you get gamma static, which is function of phi classical and its derivatives. And you can have something interesting, which is, so now just grad phi squared, and since it is gamma, we'll need a minus sign in front, and plus some u of phi classical. If you now put your favorite Mexican head potential, then you can get what, so if u is equal to but plus lambda phi to the 4, then you have u that looks like this. Then you can actually get solutions for phi which start at minus phi, let us call this phi gs, let us say. So minus phi gs and plus phi gs. So you can actually have solutions which are minus phi gs for most of the time on this side and plus phi gs here. And in between they actually interpolate as if it is, interpolate as tan hyperbolic. You can actually solve the differential equation, and instead of minus it will be plus, plus because it's actually not time derivative. So it will be plus du by d phi. You do it in one dimension, 1 plus 1. So choose only one space dimension. And if you solve this equation, this nonlinear equation has a nice exact solution as tan hyperbolic. So you can come out with non-trivial ground states. These are called kink solutions or solitonic solutions, and condensed matter physics and various, and even in optics you can find these solitonic modes propagating. So these are called solitons. So all such things can be found from quantum theory, where you have approximately classical description, which you know actually derives from some big daddy quantum theory, but after everything is integrated out, the effective degrees of freedom that remain are this phi classical. The extensive variable that remains is just the volume or just the total number. So it's like this. So this kind of expressions can be constructed. That is the meaning of gamma. And we want to see how to extract such a gamma out of our W of J. Right now we have a description W in terms of J, some external current. The answer is that gamma need not always have the naive symmetries that you see in the classical action. Gamma can break symmetry, that is spontaneous symmetry breaking. Yeah, the quantum action will not respect the classical symmetries. Okay. So it can happen in several different ways, and well, so this is actually the classic example, the phi to the 4 theory, but with a negative sign for mass square term, the square term, the quadratic term, but positive for quartic. This is potential, not action. So minus here but plus here is like this. So this theory has, let us, if I had only a real scalar field, it has phi go to minus phi symmetry. But because it is now like this, you will have to do quantum theory either here or here. You can't do it in both places. But if you do it in either of them, then you have broken the symmetry. Now you don't have the freedom to flip phi to minus phi. So then what will happen is the excitations that you see over it, the quantum excitations, will be the small oscillations here. And they are then, their interpretation is specific to having chosen plus phi classical. Somebody else can make a choice of putting minus phi classical, his quanta will be different. You will have to do some unitary transformation to convert his to your description. But those quanta will not enjoy the phi go to minus phi degree of, symmetry. So the phi quantum need not have the classical symmetries of S, and it gets a little more complicated as well, which we will see later. If Vikram is ambitious enough, he will go to what are called anomalies, where it is not even so trivial. Here at least you can even see algebraically that this happens, but there are also ways of quantum mechanics violating classical symmetries which are hidden in the loop expansion. But eventually you find that the corresponding conserved current will not. So for every symmetry, this is of course a discrete symmetry. You can, if you make it a complex field, then you will have a real part, imaginary part, real phi, im phi. Then you at least have a continuous symmetry. But there also symmetry will be broken. You no longer can rotate. But for this case, we know that there is this is just complex Klein-Gordon field. So there is a conserved current, right? It is equal to, this phi star d mu phi minus phi d mu phi star. So there is a conserved field, but a conserved current corresponding to that symmetry. But sometimes in quantum mechanics this may not work, not equal to 0. So it can happen that. So this is just for example, but it can happen that d mu j mu may not come out equal to 0. Where you have to interpret this as the full quantum expression for the current. No, it's not this. This is too simple. That's not where it happens. It happens in the case of chiral fermions. This is called anomaly. So it's a grand preview of what the whole course is trying to do. I don't mind spending a little bit of time because these ideas are all so difficult that it is okay to repeat them. But now since we have lost all the time doing this, I request you to come prepared next time, having read a particular section of Ramon's second edition book, the one on effective action.